And welcome to the desk, Ladyada.
Everybody, and welcome to my desk. It's been a little bit of a rainy Sunday. Also, we have a sick kiddo, so we're gonna make it a pretty quick episode. But I did do a lot of hardware yesterday and a little bit of today. So let's jump right into it. Okay, so let's go to my computer, and I'll show off some of these designs. So the first design that I worked on is for this board called the LTC. I keep forgetting what the screen is, smaller resolution, so I'm gonna close these. Thanks. This is called the LTC 4316. It's a very interesting chip. This is an I2C address translator. And basically what it does is it looks for like that first byte that's sent over an I2C data bus where like the controller is trying to address the peripheral, address 10 or 25 or 77. And it will XOR in a up to 7 bits of bit flipping to invert certain bits from like 0 to 1 or 1 to 0 and basically like seamlessly translate that address to a different byte. So for example, you want to connect to a bunch of VL 53L1Xs. It's like a proximity sensor, and you want like 8 of them. Well, you can use a multiplexer, I2C multiplexer, or maybe you don't want to use a multiplexer. In that case, you could use this chip in between each device, 7 of them. So like one would be the original device, and then the I2C address translator would go in between the other 7, and you would like flip a bit here and there, until you have a different address for each device. And then in your driver, you just tell it, hey, look for this address, not the original like OX29 or 39 or whatever. So the only thing that's a little annoying about this device is the way it works is that there's 2 pins, XOR H and XOR L, for high and low. The high is 3 bits, the low is 4 bits. And you have to use a resistor divider, and it's a linear resistor divider, and they're not expected to be adjustable, right? They expect you to be like, okay, I fixed the resistors, I picked 2 resistor values to fix the divider and put a certain voltage into here. And so the XOR value is, fixed in hardware, but I want it to be adjustable. So what I ended up having to do is, let's see, I wrote with the help of ChatGPT 4 a little script that will let me create, do the math to create a divider with parallel resistors, like two optional parallel resistors, and then tweak those values until I get, like, I'm not going to be able to change all 7 bits, but I could have 2 bits flippable, to be customized. So here is the resistor divider. So for the high bits, these switches can be off, and then these 2 resistors make the divider, and then I can flip either one of these on or off to create like 4 options that are paralleled with this resistor. And then, I ran it a bunch of times until I got ratios that matched up with the datasheet says are valid. Options, turns out it's like bits 5 and 6, I think, are the ones that get flipped. It's actually tough because this is resistor dividing and parallelizing is non-linear. A resistor divider is I don't know, asymptotic, I guess. I don't know. The word is, it's not a linear division because it's R1 over R1 plus R2, not R1 over R2. So, you can't, there isn't any magical combination that will let you have more than like 2 bits, basically. I tried 3 and it just wasn't working out. Anyway, so this is the design that, oh, you know what? I just realized that my clock is not working anymore. The This is the design I came up with 2 dip switches, and then if you really do need more address bits flipped, you can pick a resistor from the data sheet. They tell you which values to use to flip any of the other 4 bits. So without any soldering, you can do 2 address changes. 4 address changes, 2 bits. And then with another resistor, you can do like another 128. So it's kind of an interesting chip. So I actually spec'd this like a couple of years ago, but again, it was one of the part shortage parts I couldn't get for a bit. So I dropped it. Another thing I did is, if you remember, a few weeks ago, I talked about UPDI programming, a high voltage programmer with a 12-volt switch in it. And then we got an email from someone asking, hey, can you make a breakout just for that like analog switch? Because I want to do analog switching. And so I actually it was on my list for a while to do an analog switch breakout. So I did a couple things. One is I found that there's an I2C 1 to 8 analog switch available from Analog Devices. Desktop that does that's I2C controlled and has one input that you can select to 8 outputs. You know, it's bidirectional, but it's an analog switch. So you can do like audio or video or like signals that you want to analyze or whatever. You can switch them around. And then this is the chip. It's a TSOP, and then I just put it on a STEM and QT because I2C controllable. It's very simple. Like you literally just write a byte to the address, and that byte says like which bit is connected. Right? Like it's very simple. But I think this could still be useful. This is a five. This one is 5 volt max. Is the only trade off is it's not a high voltage switch. But there's still a lot of people I think who have like 3 or 5 volts, logic level signals that they want to switch around. So that's the ADG 728, and then there is a friend of it, the AGG 729. Same cost, almost, but not same footprint. And this one is a dual 1 to 4. So there's 2 pins, and then each one can select up to 4 different connections. So it's like a little bit different. This is for stereo, maybe. So not as many options per channel, but you get 2 channels. I think this one might actually end up being more popular because I feel like a lot of times people are using this for like stereo audio or something. They want to switch it between some sources or whatever. So I think this one could be good for that because it's a stereo connection. So that's the 2 STEM and QT versions. And then for a true just analog switch, what I did is I made a stemma version, and then I'll do the great search right afterwards. 1 second. Analog switch. In the previous video a few weeks ago, the part I picked was like basically the max 4561. I ended up going with a 4544 because it ended up being about the same technically, and the cost was pretty much the same, a little bit less. But it seemed like the max 4544 had a little bit more stock available. So this one has signal coming in through a JSDPH, and then you'll need to give it the V-in voltage has to be high enough to be higher than the voltage you're switching. So if you're switching 12 volt voltages, you need to have 12 volt power. That's normal though. And then a terminal block with the SPDT outputs. This is what it looks like. The signal determines whether the common pin is connected to normally output or normally connected. And this one can go up to 12 volts. But there's no such thing as a 12 volt compatible I2C controllable analog switch. So you can have one, I2C addressable. So it's so cool because you can like just plug and play it, or you can do, signal to control, and it can go up to 12 volts, and you can have more options. Most of these are signal controllable. So those are some of the designs that I've done. So let's go to the great search.
Where in the world is that part I need? The great search with DigiKey.
The Great Search brought to you by DigiKey and Adafruit. Thank you, DigiKey. Every single week, Ladyada is the power of engineering to help you. Yes, you found the things you need on digikey.com. Ladyada, what is on the Great Search this week?
Okay, so this week we had a request for, from me, like I had a request to make this board, but then I'm the one who's looking for the part. I'm looking for a small, low-cost analog switch that's surface mount and can switch up to 12 volt signals, but the signal that's controlling that you use to control it up and down should be like 3 volts compatible. So basically, it can use a 3 volt signal to control SPDT 12 volt analog switch. And I just talked about a few minutes ago, I was doing a design with I2C multiplexers, and I picked the AGG 728 and see view by 728 and 729. Those are I2C compatible, which is like super awesome, but they're only 5 volt max. I need that 12 volt compatibility. So let's go to DigiKey and let's look for analog switch. Okay, analog switches, multiplexers, and demultiplexers. Sounds good. Now, this difference between an analog and digital switches, this one, you know, if you put audio in, you'll get audio out. Whereas there are multiplexers that work with digital signal, but like I squared C is really common, or UART. But with those, you can't put analog signals in; it won't work. They're looking for specifically digital, like 0 to 3 volts only. This is analog switching, so it'll work with digital signals, although maybe not as fast. But it's really good for is like your potentiometer signals, audio, video, test signals. You know, apparently it's like weird. Every time I look at a data sheet for one of these devices, it says like ultrasonic, like you know, like sensing stuff where you have signal coming in from a sensor and you want to switch it around to a different location. Okay, so here's all the analog switches, multiplexers, multiplexers, about 10,000 options. So first off, I'm always looking for only active available, and I want only surface mount. So I'm going to skip the through hole, and I'm going to say normally stocking. So that gets rid of like 2/3 of the options, just because, you know, I'm not dealing with stuff that's through hole, which is like a lot of the 4066 or 4051 type. Next up, I definitely want to have the voltage for the power supply. Remember, I said that has to do at least 12 volts. So that's going to also filter out a lot, because there's a lot of 3 or 5 volt only devices. So let's look. So the only thing is that the supply, the way it's done is it has like a little squiggle telling you to and from. Here, I'll put it above my head. So you actually have to go through and like pick through each one. So for example, this one is going to work because it's 1 to 8, 1.8 to 12 volts. And then this one is 10 volts, not enough. 12 volts, 12.16, 15, 16, 12, 12, 12, 13.2, 15, 16, 16, 12, 15, 16. It's a little tedious, but go through and do them all. 15, 16. And then I want to make sure that this works at 3.3 volts. So I'm not going to keep going, because then it's like 5 to 20 volts, but it needs to work at 3.3. So these are the ones that work within the range that's valid. Okay. So now I've got much fewer, like 500 options. Next up, I definitely I don't need like some of these ones that are like multi connection and stuff. I'll say that one thing you'll notice that there's a lot in like a certain family, like the 4051s. But one of the trade-offs about these CMOS analog switches is, if you look at the data sheet, hopefully it'll come up. Okay. They will work at high voltages, 12 volts, 18 volts, whatever. But I should have popped up the data sheet beforehand. If you look at the V high for them, the V in high, which is quiescent, propagation delay. Okay, V input high voltage. In order to trigger it, at 10 volts, or if you're powering from 10 volts, you need a 7-volt signal to power it, which is not what I want. I want to be able to not power it, to signal it. I want to signal it with a low voltage, like 3 volts or so. And so a lot of those analog switches that are like the CD 4051, 4066, those are not going to work because of that issue. And there's no real way to select them out. One thing I'll say is I definitely want like an SPDT. So I'm going to just select the SPDT options, and then I definitely don't want the SPST, which is just like on off. I want to have SPDT for normally open, normally closed. Although I'll grab the DPST, I don't know, the other way around, and the DPDT also. So let's filter that out. So it gives me 100 options. And then number of circuits, I really only need 1 circuit. So let's filter that out. And now I've got 26 options. Oh, last, I'm going to exclude the marketplace just to get rid of anything that isn't immediately stocked. Okay. So now if you sort by price, you have a couple of good options. The DG419, TS 12A. So a couple different ones in the family. I did look at a bunch of these. All of them were good. I'm familiar with the Max 4544, so that's what I picked. However, I will say that like the DG419 is also totally good, and a lot of these, they have equivalent pinouts, and then if you look at the V input high, which is, hold on, I gotta find it in this. V in. Well, I can definitely find it on the Max because I remember I looked this part up. Hold on. Each data sheet, it's like you want to find the info, and it's not always in the same location. So this one, V input high. So you see it here, the V input high, no matter what the voltage is, it's going to be happy at 2.4 volts. And so that means I can trigger it for sure from a 3.3 volt signal. So I did in the end pick the 4544 just because I'm a little familiar with it and it had a lot of stock. But I'll say that the DG419 was also a good option. So you have a couple varieties that are available here. But what's nice about this is like the layout was very simple and the usage was very simple. So I'm going to try this out. I'm going to get a prototype made, and probably like in a week or two, I'll do a show where I talk about how well it worked. Maybe I'll try switching some analog signals around and see how it goes. So that's my pick for the Great Search.
Where in the world is that part I need? The Great Search with DigiKey.
All right, thanks for joining us. We had a little bit of a baby in the background hanging out, asking for bubbles, so we did that.
That's okay.
Yeah, a little baby.
It's a little bit
so
cold
we'll see
today.
everybody throughout the week this week. And more.
I'm going to go back to blowing bubbles.
And we're gonna go and take care of your kiddo. We'll see everybody next week.
Bye, everybody.
Bye bye.